And so this is about advances in JEA Optimisation Engine, in a case study from the Retrofit Plus project. And I'm going to do the case study, and Yi is going to do the rest of the work. So I see my role here very easy. And the case study is really about taking a passive house certified retrofit system onto a scaled up zero carbon trajectory. I'll explain what that means, but for now, I just want to say that Retrofit Plus project is an externally funded project by Innovate UK, and it transforms existing poorly performing buildings into passive house standard buildings. The retrofit is carried out by our industrial partner BT Passive using their T-Cozy system that surrounds the building with insulation, and Zero Carbon Lab are providing research for this project to assist the design team with the retrofit strategy. At the start of the project, the objective was to go for full zero carbon retrofit, but halfway through the project, a national scheme called Green Deal was discontinued, and the funding for renewable energy in Retrofit Plus disappeared as a result. Our revised objectives was to put the building onto a trajectory to zero carbon so that we have all prerequisites to make zero carbon when funding becomes available. T-Cozy system wraps the building up with passive house standard insulation and glazing. And the building is entirely wrapped up to below the foundations level. Then we have a mechanical ventilation system with heat recovery that is embedded in the insulation panels, and the thickness of insulation varies between projects depending on what is in the existing building. And testing and certification is carried out after the completion. This building was given to us, so that these two semi-detached houses, which are in fact attached, were given to us by Birmingham City Council, who was also a partner in the project. And the design team, the project team, carried out detailed surveys, including 3D laser scanning and structural survey, internal survey measurements to produce CAD drawings. Solid wall construction was discovered. This was ring window fines, 300 millimeters concrete. And gas and electricity bill for 2 years were obtained from the occupants. We also did 3D laser scanning from 8 different positions and stitched up the scans in such a way to create a full 3D model. And this helped immensely our industrial partner, who are based in Norwich, so this is pretty far away from here, about 3.5 to 4 hours drive, but this enabled them to actually measure up the building from their offices, and the building is actually just by Birmingham Airport. We also conducted thermal imaging that corroborated the absence of thermal insulation, so basically it's a solid concrete wall, 300 millimeters. And to start with, my PhD students did the model preparation. The objective was to carry out calibration and design optimization. And the target tool capable of this was JEA ++EA because of the bespoke objective functions. Zero Carbon Lab PhD students were involved in internal survey, and they created the initial simulation model in IES virtual environment, simply because they are familiar with that software. We teach it here as part of the course that I'm running. And then the IES model had to undergo several transformations to make it ready for JEA ++EA, simply because IES didn't have optimization capabilities at that time. So we then exported IES model into GBXML and imported into Design Builder to speed up the calibration, the creation of Energy Plus model. Although Design Builder had at that time and still has optimization capabilities, which are improving all the time, at that time it didn't have a capability to do a bespoke objective function. And for that reason we had to export this into from Design Builder into Energy Plus. And in Energy Plus we just did a very minor modification so that the only change was to select annual rather than hourly output. Okay. You're about to see a bit enlarged Energy Plus screen, the IDF editor, where we are actually just changing here to annual simulation. Okay, now setting up calibration in JEA EA, the objective function was created so that in fact it was the error, relative error between measured and simulated performance. Measured performance was obtained from energy bills, and simulated performance from simulation. And for calibrating gas energy consumption, the heating set temperature and infiltration rates were varied, and for calibrating electricity consumption, the lighting power density and miscellaneous gains power density were varied. So you can see that in a minute. A bit larger screen where you can just about see the objective functions. So the key thing is here that you cannot do these objective functions, bespoke objective functions, very easily in any other software, and they are just shown here now. So normally we expect to get something called Pareto front as a result of optimization, but in this case we were more interested in this kind of scatter plot, where we are actually very interested in the point that is quite close to the origin of the coordinate system, because that's where the error in terms of gas and electricity consumption is near zero. And we found that point, and the errors of the calibrated model were 0.17% in respect of electricity consumption and 0.33% in respect of gas consumption. And that effectively meant that the model was 99.83% accurate in respect of electricity consumption, and 99.67% accurate in respect of gas consumption. So it's a pretty good model. So this is what we need as a base case when we are starting retrofit, because we don't know what is actually there. So these parameters from the calibration are then taken into the next stage of design optimization. And the technical parameters for optimization were 3 different thicknesses of T-cozy wall insulation. We went for 150, 200 and 225. This was combined with roof insulation in pairs with wall insulation. Infiltration air changes per hour, fuel type, gas or biomass, lighting power density, and 2 different PV arrays, east side of the roof or east and west side combined. So we've had technical parameters and behavioral parameters. The behavioral parameters for optimization were room set temperature and clothing level. And now new objective functions were set for CO2 emissions and thermal comfort. So we were running that model then and got numerous results in the form of a scatter plot. And analysis of this scatter plot and corresponding parameter set was carried out. We weren't necessarily looking for Pareto points, but we were looking for a journey from a minimum intervention to zero carbon. And this is what we found, and I have annotated it here. So we have minimum intervention here, and so this was 150 millimeters, I think, insulation, then 202 to 5. And the results show that improved levels of intervention provide scope for change of behavior. Because not only that we got better thermal performance, but also we found that set temperatures inside and then clothing levels, as determined by the simulation model, were improving. So although there's no funding for upgrade of the heating system and lighting and installation of renewables, we have created this kind of prerequisite to create zero carbon. And ultimately, when you see and hear a mighty crane lifting the insulation panels into place, and insulation being injected into the panels, you realize that this is what the simulation is all about. The finished product is shown here. It doesn't look much different from the existing building. It has much thicker insulation and triple glazing, and it is very high mechanical insulation system. And this was the photograph taken in the day when we handed it over to Birmingham City Council, that was the 24th of January. I call this picture Land of Vision because we all look far into the distance. This is Paul McGrath from Birmingham City Council. This is Ron Beatty, Chairman of Beatty Castle, who's followed David O'Harahan, and then as this person from Zero Carbon Lab. That was the project, and that was the application of multi-objective optimization. Now, ultimately, what happens is that we, just to discuss what we did, we started from IES virtual environment simply because my students knew how to use it. We went from there, exported GBXML into design building in order to create Energy Plus model. We couldn't, although we very much like to use design build, we couldn't use it, and we use IES quite a lot, but we couldn't use it for this particular purpose of calibration. We didn't want to do manual calibration, but automated calibration. We then exported that from Design Builder. We exported the IDF file into Energy Plus, imported it into JEA EA. And that was the process that we applied. Now, what was my experience of working with optimization? I found that the biggest limitation was that bespoke objective functions were not available generally in simulation tools, and they are needed for calibration. If you're going to calibrate the model, you need that. And also it is difficult to get the settings right for the first time, so you really need to rerun and to get good final results. And the user is on a steep learning curve. The learning process involves trial and error, and support is very hard to obtain. But I believe that optimization is essential for moving the barriers and boundaries of building design forward. I think that gone are the days of single simulations as we know them. So this was an overview of a real project which delivered retrofitted buildings that used multi-objective optimization calibration and the simulation model before the retrofit. And the calibrated model was then taken into the next simulation round to carry out design optimization. And the process used interoperability between simulation tools, including IES virtual environment, Design Builder, Energy Plus, and J++ EA. I will now pass you over to Dr. Zhang from NSIMS to introduce you to new developments in their optimization engine. If I may just add that we are conducting post-occupancy monitoring of these buildings, and we are going to be using multi-objective optimization to actually get some building parameters calculated in that way. Thanks very much.
All right, thank you very much, Lubo. It's not very often one can have a customer do a joint act, especially with a renowned professor like Lubo. So my talk is about new development development of our optimization algorithm. It's actually quite a humbling experience after seeing so many great software being presented today. Our work, on the other hand, is focusing on the back end of simulation, either on the computing of simulation models or the development of algorithms. So my presentation will not be as visual as my predecessors. I have to rely on your imagination to make my point across. So, why is optimization hard? Actually, before I start, how many of you know what optimization is about and use it maybe? So few. Right. Let me show you this first. Right. This is a little illustration of how optimization works. The gray cloud of points are actually from a parametric study. So basically meaning run all the permutations of your model, say large window, small window, with shading, without shading, tall, low, all sorts of design possibilities in one go. With and if you plot the cost against carbon emission of all these possibilities, you get a cloud of points like that. And in this particular case, this is a tiny case, but still contains over 60,000 different permutations. And in reality, you want to see where your best design is, but in reality, it's not possible to run through all of them. With using optimization, it can help you find the right designs you're looking for. For example, in terms of cost of carbon, the designs you really want is those along this line. So, sorry, my hand is so even worse. Right. So this is the trade-off line before cost and carbon, and normally you won't be able to do better on both criteria, giving the constraints of your design. So within this cloud of points, the cases you're really interested in are just those. Okay. So simulating all those points are a waste of time. What optimization algorithm can do for you is it can help you find this line very quickly. Let me just run this. It will take a few moments to see the points. You can see optimization in this particular case. They use evolutionary algorithm, and it works on generation by generation basis. So iteration by iteration, you can see the algorithm is pushing the right points towards the line where you want them to be. And there are over 60,000 cases, but so far I have done only 52 simulations with optimization. And the right points, the solutions is already getting very close to the optimal designs, so-called. Okay, I'll have to stop it here and get back to my main talk. Now, as Lubo has mentioned, optimization is actually quite hard. Once you have tried it, you'll find it actually quite difficult to get into. The main problem is, from my experience, the first one is because it is iteration based. It means you have to run simulations again and again, and it takes a lot longer than you just run your model once. A lot longer, even with parallel computing. Because you have to say, with parallel computing, you can run 10, 50 simulations at one go. But but you have to let the optimization algorithm to run something like 100 generations. So you still equivalent to, it still take equivalent time of running 100 times. So the process is actually quite a bit longer than you use the model just once. And then it is nearly impossible to get everything right in the first time. There's always something wrong. Either your model is wrong, or you put the wrong parameter value in there, or you pick the wrong objective function. And if you realize something's wrong, you have to stop it and go back to the beginning. And you can see this with time constraints, you will struggle to get an answer you want. And the last problem is that for less experienced users, it is very difficult to get support. Lubo find it difficult to get support. It's not because I'm not willing to give it to him, because there's no way to support it. If I want to help him, the only way to do it is I do the project by myself, because every problem is different. You can't set up a problem. There isn't a formula. You have to learn by trying. So if Lubo come ask me, how do I set this up? I have to run the exact same project until I get the right answers. I can tell him how to set it up, which means I basically do the whole project for him. So this is a very common problem. So for experienced users, they have less trouble with getting support because through the learning process they become experts themselves. So they just give up seeking support, I suppose. Now why is it difficult to set up? I keep getting questions about how to use optimization tools. The first one is how to use your model in a tool or with a tool. This problem is getting much less relevant nowadays. Now IES has their new optimization tool. Design Builder has it for over a year now, and we see IDA has it, although we haven't seen how it works. So software companies are putting this functionality into their tools. So how to use it is becoming less important. The second one, which algorithms to use? For researchers who are studying optimization algorithms, this is important. But for users, what you need is not to pick the right algorithm, but rather to get one that solves your problem. So as long as our algorithm works, it takes 100 simulation or 120 simulation, doesn't make any difference. So just pick the one that being recommended to you, and it will probably work. And the third one, how to set algorithm parameters. This is very interesting, but again, first, quite difficult to answer from my point of view, but also it's less important because as long as you get your answer, then that's not the issue. The real big question is actually that: what do you optimize? We probably don't really. By default, we will know that what we want to optimize, but actually it's not that simple. There are two issues here. One is what is the search space, or what we call optimization variables you choose. You have to give the algorithm the right options so they can find it. For example, if you want to reach zero carbon status, if you don't have any renewable sources, you will never get it unless you get everybody move out of the house and turn it into a farm. But this one is still relatively easy because you know what are the parameters you can change and you want to change. So with a bit of trial error, you will get this right. The real difficult one is the second. So what is the optimization target? At this point, I would get some input from the audience, but probably no, it's too big. Let's say the most typical three, energy, cost, and comfort. So we want to minimize, in every design we probably want to minimize energy, minimize cost, and maximize comfort or minimize discomfort. Okay, that's very typical. But there are so many different ways to set this into the algorithm. You can set it as three objectives, say to minimize energy cost and discomfort at the same time, or set it as minimize energy discomfort subject to a limited cost, which means it's two objectives and one constraint, or to minimize cost subject energy meeting certain beauty regulations and the discomfort meeting certain requirements. That's one object, two constraints. Or you can have a three constraint option. Say we just set targets, and this is probably the compliance requirement, and just let algorithm to find an answer for you. From your point of view, this may not make a lot of difference, but for the algorithm, let me tell you, it does. The way you pick objectives and constraints affects how the algorithm works most significantly, actually. So this is a real tough question. And again, I have no way, there's no expert in the optimization will be able to tell you which way to set it, how to set it. The only way to do is to find it out by yourself. To do that project, to do the exploration and see where it leads to. So now it comes to what JEA is about. JEA stands it's just a shorter name for J plus EA, really. EA stands for evolutionary algorithm. That's the main algorithm we use. The conventional approach for optimization algorithm is a user set up a problem, let optimization run, normally take several hours minimum, and then check what the results is like. If they haven't got the right results, go back to the beginning and let it run again. What JEA does, and our new invention does, is make the middle part less opaque. Okay, so the user now can interact with the algorithm when it is running. So during the search process, the user can change their problem definitions, can adjust algorithm parameters, and by looking at the results they get at that point. So what they can do, which I'll show you later. Actually. So these are the 5 levels of interactivity we have to put into our algorithm. The first one is progression control. So basically, you can start, stop, pause, resume, cancel. The optimization process. This is fairly typical. I think everyone has that. The second one, you can change algorithm and settings on the fly. So when the optimization is running, if suddenly say, okay, well, I want to explore more options in one iteration, I can change the population size, and that change will take effect immediately. I think some tools you'll find this function, but it is less common. The third one, so-called optimization criteria. So JEA allows you to change objective functions and constraints whenever you want. So if you start with the 3 objective options, say minimize, minimize energy cost and what's the third one? Comfort. And after a while, you see, okay, it may be too hard to get these 3 all done at the same time. Let's set a target for cost, and then try to push down the other 2. You can do that without stopping the algorithm and go back to the beginning. And this will allow you to make mistakes of setting up your tool. I haven't seen any other tool has such function in it. So I'll probably say this is we are the first. You can probably do it with MATLAB, by the way, if you program it yourself. The fourth one is the search space. You can actually, for example, you start with a really broad search with all sorts of possibilities put in, and after a while, you come back thinking, okay, maybe I really don't want the wind turbine in my backyard. So you can remove that option, and your optimization process will just continue, and without that option, and all your previous solutions will still be there, and yeah, and you can. With more experiments, you will narrow down the field of, you will narrow down the design space and focus more on the important parameters. So the fourth one is quite useful. The fifth one is actually JEA is completely agnostic to simulation models. It doesn't know what simulation model you are using. You can actually type in numbers and the JEA will happily carry on. Which means you can make changes to evaluation at any time. This gives incredible flexibility of how you do things. For example, you can, maybe sometime in the future, you can mix design builder and IES. Run some simulation with design builder, run some simulation with IES, run some with IDA, type in some user calculator, spreadsheet, whatever, and it all goes into one optimization process, and it helps you evaluate what are the good solutions. And also, you can use this function to create hybrid processes. Like if you want to incorporate uncertainty into the optimization process, you can do a random sample with JEA and use that output as the evaluation results to feed the optimization process. So the engine supports all this, but of course, how to use them need to be implemented. And JEA lives online. I think nowadays everything's better if it is online. So I would like to call it algorithms as a service. So it's essentially the software as service model. But since this is a purely a algorithm and it gives you all your project data, our servers, which you can access from any point. So this enables collaboration. You can start a optimization process in the office and go back home and check its progress on your phone, or you can pass it on to your colleague and they can make changes and carry on the working.
Well, about 8 minutes to go, yeah, okay.
Thank you. So this is really quite a very useful thing. I think I will go to a demo first. So just okay. I'll show you an example and see how quickly I can do it. This is a very simple example problem. So there are only two variables, x and y, and the objective function is t1 is just 100 times x, and t2 is 100 times y. And the circle in the middle is what I call a feasible area. So all the variable solutions we want to be there. It's trying to minimize T1 and T2. So the red line shows where the results we want to find in the end. What I will show you is how to do that search. The first one, I don't think I have time to ask you to think how to do it. But the way I would do it is first do a course grade search, do a pattern search, and cover the whole area. And if I see some interesting points, I will narrow it down with a finer grade and to search a smaller area. And this may still not be refined enough, and later I'll run optimization in that smaller area. hopefully, if it works, you will see how this interactivity helps. So in the end, hopefully we will get to that line. Okay. Now, since I'm a bit tight with time, so I have started this project and have done my first grid search already. You can see this is from 0 to 100, so that's 100 times the variable value, and this one is the same. And those are the points. So 10 points on each axis, but the real problem is actually 100 points on each axis. So what I'm going to do, so what I'm going to do now is to reduce the search space size and run it again. This interface looks a little crude, and this is by intention because what we're offering is the engine. We want you to find ways to use it, and this shows how the engine works. So what you need to do is actually just send text-based command. So these are all the settings you need for that optimization engine to work, and then make changes to it. I need to change that to update because the project is already there, and I need to refine the search space. I think this time I use 0.05. Helping with the unsteady line, I think. And we're still doing a parametric run. And let's see, let's send update command. And if nothing happens, I will cry. Okay, there's some error in there. I think, given the time limit, I'll just give up on this. And if you want to, I can show you online later afterwards.
Add quotes, maybe.
Oh, I see. Good. I should. See, that's why Lubo tell me don't do a live demo. Well, let's see if it works. There we go. So it's updated, and let's start it again. Okay, it's launched. Let's go run. Let's keep this part. So this model is actually running here. You can see the JavaScript of that model. So it's just calculating 100 times x and 100 times y, and send it to the server. And you can see it's taking cases from the server. And you can see the cases is taken like that, and calculating results before it's sending back to the server. And you can change all those using this interface. And on this process, if I change out update, it should give you a few more. Wait, I think I didn't change the range, so it's actually still searching the whole space, but with a finer steps. You can see the points there. It should have been smaller. But let me stop that and change to optimization this time. Let's see if it does.
Just 2 minutes now.
I know. I know. Told you I tend to overrun. But okay. Come on. Other responses. Out of it slowly. Okay. So it should be running optimization now, and in a little while you will see more points hardly along this line. Okay, I forgot to change something else. Horrible. So I should have changed to define this grade, so you will see more points. But still, with optimization, you will see points showing up here more than in other parts. So this at least give you an impression how this can be used. The last thing to show you is our next version of JEA. I told you the interface is very bland, but what it does is it can now optimization projects are actually running online. So on my local machine, I don't have to store anything. So I can find a project that have been running there and just retrieve the results. And you will, and from there, say for example, if Lubo started a project and give me access to that project, I can see exactly what he has done. So if he wants support, I can check how everything's going and give him advice straight away, rather than start from scratch trying to figure out how to do it. So, and all the models are, in this case, all the models are stored in our servers and retrieved to the local computer when you join the project. So I think that concludes on my presentation. And yeah. For that example, if you can scan this QR code, there's a little app where you can view the project is just run in the web browser. And this means basically you can develop different interface for different users and give them access at different levels. So some create project, some can make changes, some can view the results. And that's
Thanks very much for that, Ian.
Thank you very much.
You've kind of mushed the timetable a bit, but we'll let you off for that, for the interest. Any brief questions? So we might take one or two. No? There's one question across there. Oh, it's Andrew again.
Yes, this is definitely our next step, because once you run so many simulations, you do see pattern emerging. And one approach, I'm pretty sure some of you will have heard it, is called surrogate modeling. So by running a good sample of your cases, and from that you can extract simplified models like artificial neural network models, and use that in place of the real simulation to save computing time. And JEA will support it very well because it doesn't care if it's a real model or a surrogate. And you can mix both and play all sorts of funny things. Yeah.
Okay, one more. No, I'll leave it at that. Okay, thanks very much, chaps. Remember applause for the teacher. Right, we're on.